name is Clotilde Philippe, and I'm a PhD student at ENSCR under the supervision of Yann Troelles and Loïc Lemiègre. So today I'm going to present you my PhD work about the synthesis of enamide, formation and study of fluorescent tetracyanobutadiene. So first of all, TCBDs are the product of the reaction between an electron-rich alkyne and tetracyanoethylene, so short for TCNE, by a 2+2 cycloaddition, then a retroelectrocyclization to give this TCBD motif. So this reaction have been known from now several decades, and a large number of electron donating group have been tested and shows that the reaction works quite well with ferrocene, aniline, thiophene, and so on. So TCBDs are interesting because they have exceptional optical properties. So they have intense linear and nonlinear absorption, but they are generally non-luminescent. There is only a few examples that show luminescence in solution at room temperature, and they have quite low quantum yield, less than 4%. The reason why they are generally non-luminescent is due to very efficient non-radiative deactivation. This was proved by calculation for those two compounds. So we can see that we have a deactivation by the rotation of the TCBD. So our group is interested in the reaction between enamine, so this compound, and TCNE to form this new kind of TCBD. So we were able to show that this reaction works quite well with a lot of substrate. Even if with some electron withdrawing group, we have a lesser yield, but we can increase the yield by increasing the amount of TCNE. So during the investigation of this reaction, we were able to see some unexpected luminescence properties. So you can see that for this compound, we don't have any luminescence of the solution, which is a mixture of cyclohexane and dichloromethane, but we have luminescence of the crystals. For this other molecule, we see that we don't have any luminescence in dichloromethane, and by increasing the amount of cyclohexane, we have an increase of the fluorescence, the quantum yield. So we see that this kind of TCBD have a luminescence sensitive towards the environment. So my project is to synthesize more TCBD from enamide bearing diverse fluorophore on this position. So I've worked with perilene, anthracene, and some derivative from fluorine. And we are trying to understand their luminescence behavior, which is luminescence in powder, but also in solution. So first of all, let's talk a bit about the synthesis. So for the purine TCBD, we decided to do the formation of the enamide in Evanus condition. So to do that, we started the synthesis with the purine, and we did form the aldehyde on this position with 29% yield. And then we form our gem de Beaumont vinyl with 97% yield, which is the starting material for the Evanus condition, which is a copper catalyzed reaction that gave us our enamide with 50% yield. Then we were able to form our TCBD with 71% yield. So another example is the anthracene TCBD. So here we are working with Thun condition for the formation of the enamide. So we started the reaction by a Sonogashira coupling on the 2-bromo anthracene with 86% yield. Then we did the deprotection of this alkyne with 5% yield, and we then form the bromo alkyne with 78% yield, which is the starting material for the Thun condition, who is also a copper catalyzed reaction that gave us our desired enamide with 71% yield. So when we put this enamine in reaction with TCNE, we didn't get the desired TCBD, but the product of the disalder on the anthracene core. And by adding another equivalent of TCNE, we did form the TCBD, but we still had this Diels-Alder reaction on the interesting core. We also showed by reacting our enamide with 5 equivalent of TCNE, we can directly get this compound with 73% yield. So now we try to recover our interesting core. So to do so, we try to do retro Diels-Alder, and we did put this compound in dioxane at 80 degrees, and we did observe the liberation of TCNE, but the equilibration of this reaction does give us only 14% yield for the anthracene TCBD. So we decided to add some scavenger to catch the released TCBD. So we choose this aniline compound, and by catching the TCNE and form this TCBD, we were able to get our anthracene TCBD with 76% yield. So to understand better this reaction, we also made another example with the diphenyl anthracene TCBD to see if we have also a Diels-Alder or not. So we started with this diphenyl bromoanthracene and did the Sonogashira coupling with 88% yield, and then the deprotation and the bromination to be able to perform our enamide with 89% yield. So then by adding 1 equivalent of TCNE, we directly get our TCBD. Due to the steric index of the 2 phenyl group, we don't have the Diels-Alder on the anthracene core. So the mechanism for those 2 reactions on the anthracene were deciphered by theoretical calculation by Trevor M. So I was able to synthesize a large amount of TCBD, so with pyrene, perilene, anthracene, phenanthrene, triphenyl, and some derivative from the fluorine. And I did the UV visible analysis on this compound, but also the measurement of the fluorescence in solution and in solid states. So for the UV visible spectrum, we can see that by changing the fluorophore on the TCBD, we can modulate the maximum of the first band absorption. So we can go with the triphenyl compound for 440 and to 540 for the pyrene and anthracene, and up to 640 with the perilene compound. For the fluorescence property, we can also modulate our emission maximum by changing the fluorophore. As you can see with fluorenon, we have an emission at 534, and with the phenanthrene, we can go up to 648. Which is also quite remarkable is the quantum yield of this triphenyl TCBD, which is at 8%. And it's, to our knowledge, the best yield ever reported for fluorescent TCBD in solution at room temperature. We did also the measurement of the fluorescence in powder. And we can see that by changing the fluorophore, we also can modulate the emission. And this time in solid state, we can have an emission up to the near infrared with the pyrene and the perilene TCBD. So to conclude, a large number of fluorescent TCBD have been synthesized. Their emission in solid states and in solution can go up to the near infrared region. We can modulate the emission maximum by changing the fluorophore, and we can have a quantum yield up to 8% in solution at room temperature. The next step to understand this phenomenon will be to do more analysis like time resolved fluorescence and transient absorption, which will be made in collaboration with Antti Brie and Nathan McLenagan in Bordeaux. So I will also like to thank all the people that have worked with me on this project, but also you for your attention. Thank you.
Thank you very much, Clotilde. So we will take only one question, and if there are more questions, you will be able to ask them at the end of the lecture by Phil Castellano. So are there any questions? So if not, Clotilde, stay tuned, and maybe there will be question in the chat or at the end of the lecture.
Thank you.
So now, Phil, you can unmute yourself and you can start to share your screen. Yes. So I will make only a very brief introduction. So Phil Castellano is professor of chemistry at NC State University. He's interested in various aspects of photophysics linked with energy transfer, solar fuel catalysis, light-emitting diodes. And today he will talk more specifically of photochemical upconversion. So please, Phil, the virtual stage is yours.
Okay, thank you, Pierre-Antoine, and thank you very much for hosting me at REN today. It's really a pleasure to be here, and it's great to see so many people in the audience that are friends and former coworkers, and hopefully one day we'll actually be able to see each other in person very soon. So today I kind of promised everybody, because it's kind of late in France at this point, that I would keep this on the shorter side. So I think most of you are familiar with photochemical upconversion, and it really photographs incredibly well, as you can see here. And I will discuss exactly how all this is happening. But for those of you that are not necessarily familiar with the field, here are a number of reviews that the group has written over the years that sort of lays out how to think about this problem. And how to address it, sort of from the design perspectives from the molecular energetics. Some contact info here, which is more important because I have 3 postdocs that currently are leaving the group in the next. They're leaving the group in the next couple of months, so I have like 3 postdoctoral positions available. Just feel free to email me down here if anyone is interested. So the concept of photochemical upconversion is really began with this paper from Parker and Hatchard back in the early 1960s. But the way that you execute this chemistry really hasn't changed since it was first proposed in 1962. And the way you really do it is you have a sensitizer. And in our case, the molecular sensitizer was a metal to ligand charge transfer complex that was based on a ruthenium chromophore. And it has also an acceptor annihilator molecule. And our first pass at this was using anthracene. So what happens in terms of their electronics and their energetics? Well, the singlet triplet levels of the sensitizer here, as you can tell, really get sandwiched in between the singlet and triplet levels of the acceptor molecule. And really, as long as you fulfill that energetic criteria, in addition to making sure that 2 of the sensitized triplets can actually add their energies to put you on the singlet surface, you're almost guaranteed to fluoresce out a photon from this process. And here, this is literally this combination of these chromophores. As you can see, the green light goes in and blue light comes out. And what's really going on is the low energy absorption is being selectively, by selective excitation of this ruthenium chromophore. You make 2 singlet excited states in the solution, they'll intersystem cross to make the triplets. You'll get triplet energy transfer to occur to these anthracene acceptors. And then what happens is, this is now a kinetic phenomenon. The triplet anthracenes live for a really, really, really long time. And that allows them to have the ability to diffuse and collide with each other. And therefore, they engage in another energy transfer reaction, which is called triplet annihilation, or TTA. And that generates the singlet excited state. And that's exactly what is going on in all of these pictures. So stoichiometrically, you can kind of see that you have to absorb 2 photons and you can get out 1 acceptor. So the theoretical maximum efficiency based on absorbed photons here is only 50%. And then what does the data look like? Well, again, this is what's funny about this field. You're doing photochemical upconversion, so you're exciting here, and then you have to turn your detection anti-Stokes with respect to the excitation. So you're really doing the fluorescence experiment backwards. And if you kind of see what we're doing here, we're coming in with a 514 nanometer light beam to selectively excite the ruthenium complex. And that's about here. And then we look backwards as a function of incident laser power. And you can see what happens. As you increase laser power, we're making more and more and more fluorescence from anthracene. And I think everybody in the room is convinced that, yeah, that's the fluorescence spectrum of anthracene. And under optically dilute conditions, you can actually see this by the naked eye. Very low laser powers are necessary, and when you plot the integrated data versus the incident laser power, you see that you get a quadratic dependence. The quadratic dependence is illustrating that this is a 2-photon process. So when we embarked on this a little bit deeper, our first improvement was really to, instead of using anthracene, which is a 30% quantum yield fluorophore, to use diphenylanthracene, which is almost quantitative. Once we did that, it then became really obvious that this worked incredibly well. It worked at such low power that we could see this quadratic dependence really from zero, like from a little above 0 to 1 milliwatt of power. So this is just demonstrating again that photochemical upconversion is really very easily visualized and can be generated in a very facile manner. And that was sort of our whole approach for many years when we started doing this. And we were interested in always driving the excitation power down as low as we could possibly get it. So that ultimately led to being able to do this with lamp excitation. So literally the xenon lamp in the fluorimeter passing through the monochromator with a long pass filter, and you could literally generate upconversion in diphenylanthracene using a metallated porphyrin as the photosensitizer. Now, the choice of metallated porphyrin was, again, to increase the lifetime of the sensitizer, which then impacts the Stern-Volmer process to the point where you see what happens here. If we bring this number up high enough, we can really lower the quencher concentration significantly. And then everything can be done in the fluorimeter and you don't have any interfilter effects. So this was really, kind of as we were evolving, we kind of recognized that, okay, the lifetime of the sensitizer, you want that as long as possible so that you can basically get as efficient quenching as you possibly can at the lowest possible acceptor concentration. And then you can actually get all the light out of these solutions. And that was our whole approach for many years. And then, of course, that led to being able to see this using sunlight pass through long pass filters. And really, optically dilute solutions, you can see this very readily. We even did it inside the office back when I was in Bowling Green. And back then, it was very hard to get a sunny day in Ohio. So these were very challenging experiments because you didn't have the experimental conditions necessary to get there. But then as you kind of progress in this field, and I'm doing this to give everybody a sense of sort of history, but also our thinking. And the thing that you recognize immediately is that we were always getting quadratic power dependencies. And it became obvious from work Manguzzi did that you can actually get this to go linear. And then we questioned, is it possible to get it to go linear at solar flux? And the idea really was you have to understand exactly how this works. And the idea is that the way my group was doing those experiments for many years was in this regime, which is the weak annihilation limit. We were basically using optically dilute solutions and we were generating photon upconversion, but it was always quadratic with respect to excitation power. What you really want for most efficient reactions is to be over here. where you basically absorb all of the photons so that your rate of light absorption is the thing that really dominates this process. And you can get the rate of light absorption as high as possible. You make as many sensitized triplets as possible, and that gives you really the highest yields of upconversion. But the way that you do this is normally you have to crush this with optical power, which is what some groups do to the present day, or you have to get away from optically dilute solutions and you have to use relatively concentrated, chromophore solutions to get this to happen. And you get this to go linear. And ultimately, once we sort of understood all of the operating parameters, and you can see there that we started in 2004, and by 2012, I think we actually understood finally what we were doing. So it took 8 years. And then we started recognizing, oh, now that we understand everything, we can really open up the types of sensitizers that are being used in the way you design experiments. So we then had this epiphany in the group that we needed to go to earth abundant photosensitizers. And what's a great place to start, and this is what's so appropriate, is of course, this is Jean-Pierre Sauvage's like early copper-1 complex. From back in the early 1980s, the DPP complex, and we demonstrated in this paper in ChemCom many years ago now, that you can actually do effectively, red to blue and red to green upconversion. Again, aromatic hydrocarbon perylene, but then we showed you could do this with a Bodipi dye, which many of you in this institute are familiar with. And the idea is once you understand how to do all of this, you can then start to recognize that you can use almost any chromophore under the sun to execute this properly. And I won't get into all the details here because I'm going to save the details for a little bit later. But this is giving you an idea of all of the design elements that we put into copper-1 photosensitizers, and a lot of this was based on some of the original Sauvage procedures, and then some of the things that Dave McMillan at Purdue had done to reinforce steric hindrance. And we designed a lot of these molecules over here. And really studied them in depth, because what we were trying to do was, how do we get basically the smallest possible Stokes shifts in these molecules, getting the highest or longest possible lifetimes, and having really good visible light harvesting. So all the things you want in a photochemical upconversion photosensitizer. And then my group also does a lot of ultrafast spectroscopy, which I'll just skim over right now. But the idea is that the more steric hindrance you impart in these molecules, which means effectively the least amount of pseudo-ion Teller distortion you enable these molecules to engage in their excited states, is going to be beneficial to basically shortening these ultrafast time components. And the more you shorten the ultrafast time components, typically that is telling you that you're not distorting as much, and that improves your Stokes shift. So all the ultra-fast data informs what's going on longer timescales, and then you realize, oh, you get very long lifetime copper-1 MLCT excited states by doing this. And the reason why it goes into this crazy flattening distortion is because it's a metal to ligand charge transfer excited state. So you oxidize copper-1 to copper-2, and of course now it becomes denying, and it distorts to basically relieve the non-degenerate, or it wants to basically result in the fact that you have to stabilize that paramagnetic species that you make. So that's, in this particular case, it's a pseudo-ion Teller distortion. But anyway, what you then recognize is all of these design elements then go into the fact that you now have metal ligand charge transfer absorptions, but look at, and everything is color coded here, but look at the extent of the Stokes shift changes we engineer in these molecules by really sticking in this particular case, the champion compound was putting branched alkyls in the 2,9 position, and then having sterically reinforcing methyl groups in the 3,8 positions on phenanthroline. That gives us the very smallest possible Stokes shifts. So these are the most energetic MLCT excited states we can design. And there's a lot of other things here, but you also recognize that the molecule in the ground state is actually not really as distorted as the other two. And then this translates into the long lifetime that you want to make it an effective triplet sensitizer for photochemical upconversion. So back when we were doing this, and this is now 2015 with Kate McCusker, we kind of systematically looked again at a number of aromatic hydrocarbons just to show with this particular copper photosensitizer, we could actually get pretty good KSV values and then, you know, about an order of magnitude below diffusion limit, but we can get really good Stern-Romer quenching. And then that translated into exactly what I was telling you before is under, you know, different conditions, we can go from this quadratic to linear power dependence, but then you can actually measure the upconversion quantum yields. And in these first two cases, they're not very good. But in diphenylanthracene here, you can see that we maximize that 17%. And at the time, that's actually better than any of those ruthenium compounds we had started with. So the point being, once you understand sort of how to control everything and understand the different power limit regimes and how to control those power limit regimes with absorption and kinetics, then you really can design very effectively or very effective photochemical upconversion reactions. So, you know, to kind of put this in a different perspective, here's this transition between quadratic to linear. If you put it in terms of a double logarithmic plot, it's very easy to see. And then there's some other things that we started to recognize. So if you have higher concentrations of anthracene, for example, you actually will move the power point of where you actually see some of this because the quenching efficiency changes. It's more efficient with higher anthracene concentrations. But there's another thing that really was pretty interesting in doing all of this. At higher anthracene concentrations, we also have really high ground state anthracene concentrations. And we saw a cycloaddition reaction in the student's presentation earlier. This is now a photocatalytic photosensitized 4+4 cycloaddition of anthracene. So you selectively excite the copper complex, and really what you start doing is you precipitate out the dimer of anthracene, but it's sensitized to visible light and it's completely photocatalytic. So this is interesting because it gives you a means for doing solar chemical to thermal energy storage. Now, why is it thermal energy storage? Well, it comes down to the fact that this chemistry of the cycloaddition is usually run with ultraviolet light to make this 4+4 dimer. The 4+4 dimer is interesting though. If you melt it, the melting actually ends up being exothermic. So this is storing energy because this molecule is actually metastable. So this is a really interesting idea that you can take sunlight and drive the triplet sensitization reaction. You get triplet annihilation, but then the singlet excited state that you make, as long as there's a ground state to intercept it, you do the 4+4 cycloaddition, making the anthracene dimer. And then, of course, this is the thing that precipitates, so you can store that. And the idea is, even with other derivatives of anthracene, like we have here, you basically can store or use molecules that have higher energy values. So in this particular case, you can get up to over 200 joules per gram of dimer. So I think there's something interesting to do here. We haven't quite done this yet. Okay, so kind of more into modern times, just to give you a sense of some of the things that we're doing now. I started working with Karsten Milsman and his student Yu Zhang at West Virginia University a couple of years ago. And they designed these beautiful zirconium-4 molecules, and zirconium-4 is D0. So these are ligand to metal charge transfer excited states. They're a little bit trickier to understand though, because they have some ligand-centered characters as you can kind of envision over here, looking at the electronic structure. But the interesting thing about these molecules is that they have these incredibly long excited state lifetimes and very small Stokes shifts. So we saw this immediately, and we're scratching our heads because Karsten and a student reported that, you get this thing that looks like singlet fluorescence, no question about it. But this lifetime was about 325 microseconds at room temperature. So, everything inside me told me that's not fluorescence. There's something really interesting in here, and it's likely a triplet. So then we came on the scene and looked carefully at one of these molecules, and really same idea that you sort of think, that you have a singlet absorption because the extinction coefficient's over 20,000. But then you have, like, again, something that's not really Stokes shifted, but then the exponential decay that you get from this luminescence is 350 microseconds. So no way is that, pure singlet fluorescence. So it turns out these molecules, if you just look at the temperature dependent luminescence spectra, what you really gather from this is as you heat it up, see what happens at high energy, you're cranking up the intensity. That's a clear indication of thermally activated delayed fluorescence. So it turns out at the coldest temperatures, the triplet's the only emission you see, and it sits here about 640 nanometers. The singlet is here about 590 nanometers. And, in essence, you can see it spectrally. But then we also fit the observed rate constant as a function of temperature, and very clearly follows this Arrhenius behavior, which can then be fit to sort of the standard model that's used. And this demonstrates that this is a clear indication of TADF from this ligand and metal charge transfer excited state. And it has a single triplet splitting of only effectively 1,700 wave numbers. So it's a really cool concept to think, and other people have done this in the literature, including my own group, that you can actually think about using TADF photosensitizers in photochemical upconversion. And that's exactly what we decided to do. So my group also at the same time decided, let's make some variants of diphenylanthracene to see if we can make something that might annihilate more effectively. And we did that, and we made this series of compounds really based on carbazoles here. And the idea really was simple. Can we, kind of make these molecules, have them with high fluorescence quantum yields? We do absolute quantum yield measurements, so this is actually good to 4 significant figures like it's shown here. So these are all very good, but still not as good as diphenylanthracene. And ultimately, what was good about this was all of their emission spectra fit in the minimum of the absorption spectrum from the zirconium-4 photosensitizer. So that was our thinking, is we can do upconversion of effectively green to blue, and it spectrally fits in the minimum absorption window from the zirconium complex. And that's exactly what we did. Here's all the calculated energetics that we actually did. Here's the spectra of everything. And through a long pass filter, very clearly, you can see the photochemical upconversion, and it looks really, really bright. So the thing that doesn't go into these talks, which needs to, is that there's a battery of spectroscopic techniques that demonstrates every step of this reaction I'm telling you about. So we understand the quenching in every single case so that we can figure out the quencher concentration to use in photochemical upconversion. We demonstrate with transient absorption that we get triplet energy transfer in all cases. And then we actually do time resolved photoluminescence to demonstrate that we see, delayed fluorescence at higher energy coming out from each of these acceptor molecules. So there's a massive battery of experiments that goes into this. So this is the first data we ever took in my group in a photochemical upconversion experiment. Even though we absolutely understand how to optimize everything, we optimize everything, and then we measure the incident power dependence. And I think everybody here should notice something. The slopes of every single one of these is 1. There is no quadratic dependence going on anywhere at the lowest incident powers we have. And to give you an idea, this is even down to 3 microwatts, 2 microwatts of incident power. So of course, when I saw this data the first time, I told my student, you know, I don't believe it. You're exciting this directly with UV light. You're doing something wrong because there's no way that this is happening. So we reproduced this probably dozens of times, and I finally had to start believing it. And then recognize something else. Let's actually get away from the optimized quenching conditions. Let's drop the triplet energy transfer reaction from the Stern-Volmer analysis. Instead of working at like 95% quenching, let's knock it down and see if we can move the ith power point, which is the conversion from quadratic to linear. And then when we did that, we were able to see with our experimental apparatus that we could actually definitely now see quadratic to linear power conversion. And the ith, which is this point here where these lines intersect, is 2.3 milliwatts per square centimeter here and 0.72 milliwatts per square centimeter here. So that really illustrates again that we have that sensitized TTA mechanism. But you can kind of see the problem we have. We can't really get a good optical measurement to like these incredibly low optical powers. So that was a challenge. So then what we said was, okay, well, if we assume that the original Manguzzi work and then some of the work from some other groups here really illustrates the fact that this ith point is really related to the first order triplet decay, the second order triplet annihilation decay, the quantum yield of the energy of the triplet energy transfer, and then the absorption coefficient of the sensitizer and its excitation wavelength. So you kind of see that this is an oversimplified expression for where the ith point should be, but we have this fixed in our experiment. This number is fixed in our experiment. This one is fixed too because we use the same sample absorption. So we actually can change that, which I just showed you. So if we change this efficiency, we just kind of assume, let's do a ratio. And really under the optimized conditions, we took a couple of measurements. We know what the ith point is. So then if we now have the system optimized, we can solve for the unknown. And it actually shows that the ith point in our samples should really be at 115 microwatts per square centimeter. This is why we really couldn't see any quadratic dependence in our work, because we can't measure the optical powers to that low level. And I think this just illustrates the fact that we're able to do this with the zirconium-4 sensitizer in unprecedented fashion. So then if you now go to the quantum efficiencies, what you get from this, and this is absolutely amazing to me, all four of these acceptors really gives you amazing quantum yields for upconversion. Diphenylanthracene always wins. You can't beat it. But we tend to think like this 42.7 number is probably close. It's really within experimental error, probably closer to 40, which then kind of makes sense because that's about what you can manage to get as a maximum efficiency if you make a bunch of assumptions in the way the triplet excited states are recycled, which I won't go into. But the interesting thing is, see how the upconversion efficiencies actually seem to scale with the fluorescence quantum yields of each of the requisite compounds. I think that was the thing that was the most interesting to us. And then ultimately, these numbers here were actually better than anything we were ever able to measure before using charge transfer photosensitizers. And, you know, basically for us, we see this zirconium-4 sensitizer just seems to be the best thing my group has ever used for annihilation upconversion. And the reason why it works, and this is, again, I'm not going into a lot of details, but we went to extensive lengths to demonstrate that there's zirconium compounds do not have any deleterious side reactions going on. So they don't annihilate with each other. They don't pi stack. They do not have any weird intermolecular interactions. And we did all of this with you know, basically 1D and 2D NMR experiments. So the zirconium sensitizer is pretty exciting to us, and we're continuing to work with Karsten's group on these things. So now on a more practical side, and Auntie Bui, you know, was involved in some of this when she was in my group. And this is this concept of using visible light to initiate polymerization through this homomolecular triple-triplet annihilation mechanism. So what is that? Well, porphyrins, when you make their triplets, they self-annihilate. Everybody likes to ignore this in the literature, especially in the upconversion literature. But this self-annihilation can be leveraged to make the S2 excited state in the porphyrin. And if you use zinc TPP, you can visualize the S2 excited state formation by its fluorescence. So this is one of the few porphyrins that actually has Serre band fluorescence that comes from it. It's from an upper excited state. So it breaks Koch's rule. But this S2 excited state is more energetic, so the electron from it's more energetic, and that can be used to reduce acrylates to induce free radical polymerization, which is, you know, basically a chain mechanism. So if you have a radical chain mechanism, the nice thing about it is you really just need one radical to get it going, and then it just persists, which is really awesome. So the way that, you know, you kind of have to just look at all the spectral properties here, and I think most people here understand that, is here's the Serre band in blue, and in the red is the Serre band fluorescence. It's very short-lived, of course. It's only a few picoseconds, but I'll show you how to get around that. And then the Q band absorption is here, and then that's the fluorescence from the Q band. And this is the S1 excited state. This is the S2 excited state. So you see the energetic differences. So when the triplets annihilate, you basically make the S2 excited state, and then that fluoresces out a photon that is very easy to observe. And we weren't the first to do this. There's the Russian group, or the Soviet group was the first to do this. And then there's several papers from Ron Steer in Canada that also shows that you can do this, this self-annihilation with porphyrins. So energetically, what's going on is really shown here, just to show you that if we tried to do S1 excited state to methyl acrylate, which is our surrogate acrylate acceptor, it's uphill. The triplet's more uphill, so that's not going to work. But if you use the S2 excited state, there's actually an exothermic reaction, so their electron transfer from this excited state is favorable. So that was the thing that we were thinking about. The idea originally came from Eric Vothny's group in Switzerland. They showed S2 based electron excited state electron transfer from zinc TPP back in 2002. So the good news was there was literature precedence for this excited state electron transfer. So here's my student Nancy, who worked with ANT on this project, and she's just going to show you how trivial it is to make polymer gel objects using this 532 laser pointer. And literally a couple of seconds in that sample, you can see that we make a solid gel. If you hold the laser on it a little longer, the gel actually gets harder because you're cross-linking it more. And in this particular case, we're using TMPTA, which is over here. So it's a triacrylate. But you can kind of see that it's very easy to make a very large and well-controlled object from just using visible light excitation. And we know that this is the mechanism, as I'll show you in a little while. But really remarkable that you can do this. And you know, and Auntie's contributions were that she was able to actually do this photochemistry in a confocal microscope and really draw lines, draw the NC State wolf is what this guy is. And, you know, obviously you have to do your school logo. And you can do masking. So this is photolithography just with a non-coherent light source in the same microscope. So you can make macroscopic as well as microscopic objects using this concept. So the way that we really got into this mechanistically, and this is the only, experimental apparatus I'm showing you, is how do you measure singlet fluorescence to down to single picosecond time regime. Well, the only way to do it is to actually do, femtosecond optically gated fluorescence upconversion, which really is a state selective technique for the singlet. So this is an ultra-fast experiment. So really what happens is you generate what's called the gate pulse. So this is the direct 800 nanometer light that comes out of a Thai sapphire, and that goes into a some frequency crystal. We can change the time delays by changing the delay line here, and that is the gate pulse. We take the frequency doubled gate pulse, bring it into the sample fluoresces, we collect the fluorescence through parabolic mirrors, and then focus it into the same some frequency generating crystal. And you basically get the two-wave mixing here, which generates the UV-based upconversion signal, whose intensity is really proportional to the gate pulse and the fluorescence. And since the fluorescence is the only one of those signals that has a time-dependent intensity, the time-dependent intensity in the upconverted signal is proportional directly to the fluorescence decay time. So the way that this looks experimentally is for example, in toluene, we can actually directly excite the Surrey with 400 nanometer excitation. And if you don't have the TMPTA present, you see that is the lifetime, and it's really 1.5 picoseconds, which is nothing. But then we add TMPTA, which is a pure liquid. So in a pure liquid, you can get ultra-fast quenching. That's the trick to all of this. And if you add that, you see that the lifetime shortens. So this is a dynamic quenching phenomenon. You can do this as a function of the TMPTA, but notice it only works at very high concentrations. But again, it's just showing you systematically, we get lifetime changes. And of course, the quenching constants are above diffusion limit because the solvent quencher is basically right there to accept the electron. So this is showing us that we get dynamic quenching from the S2 excited state in these porphyrins, and it's really quite remarkable. And then we also show that it's the Surrey band emission that gets quenched in a steady state experiment and not the Q band emission. And again, it follows the same trend where it's way above diffusion limited quenching. So that is, kind of the general idea. We use methyl acrylate in these experiments because TMPTA tends to polymerize, and then it gets really complicated to remove the polymer out of your cuvettes. So if you use methyl acrylate, you keep the polymer growth to a minimum, and you don't get these massive precipitating macromolecular objects that are hard to remove and stick to the glass or stick to the quartz of your cuvette. So again, you can see this very easily with steady state quenching of the S2 fluorescence, which anybody can do. You don't need to do this with a fancy femtosecond upconversion spectrometer like we have, but you can do this with just steady state emission quenching, which I think a lot of people might pick up on because you don't think about doing chemistry from upper excited states in many instances. Okay, that was all I wanted to say before I acknowledge a few people. I just wanted to bring up, I'm also the editor-in-chief of Chemical Physics Review. So if anyone here is interested in submitting either an original research article or a review in some area that's basically physical chemistry related, please inquire to me or to anybody on the associate editor team here. Everybody's very happy to help. These are sort of some of the subject areas that we are typically looking at. So I hope to be able to speak to some of you about maybe highlighting some of your scientific achievements in CPR. We're also hosting what's called a Horizons Conference, Photonics and Chemical Physics, and that's going to be in September virtually. It was supposed to take place at NC State, but it cannot. We're doing it virtually. This is the website, so it's really just Photonics and Chemical Physics. It's exactly the title. And then to give you an idea of who's helping me out with this, just to show you, Chantal was involved in this from ENS Lyon. And then, we have Matt Beard from NREL, and then a series of other folks, mostly from the Research Triangle, because we thought the conference was going to take place in Raleigh, but it won't, unfortunately. But if you're interested, the registration is very cheap, and they're going to do an entire session on publishing, and that is going to be very valuable for graduate students in particular. And Ferdinand Grozima is going to lead that discussion he's from UT Delft. I think most of you know who he is. So without going, line by line here, everyone highlighted in the sort of NC State color has contributed to this project over the many years that we've been doing it, because we started doing photochemical upconversion in 2003. So it's very hard to get everybody on here. Here's some more people, again, even back to some of the original people that graduated many years ago, as well as some visiting scientists. So be nice. Again, we should be able to take another picture soon. This is the research group in 2020, right in winter of 2020. I think we took this picture in February, so it was right before the pandemic really hit. I think you've already seen several of the people, or I've already mentioned several of these people's names. And the people that paid for all of this work really was DOE and BioLec in particular in this particular presentation. And with that, I will be happy to answer any questions. I tried to keep it short. I hope I did it, Pierre-Antoine.
That's perfect. Okay, so thank you very much for this very nice lecture. And so the session is open for questions. So if you have questions, please, turn on your camera and unmute yourself. Or if you're too shy, just use the chat and feel free to read the question and answer. So I can start with the first one if the audience is very shy. So you mentioned the TADF effect with the zirconium complex. Did you consider using TADF, purely organic TADF sensitizers?
Yeah, in fact, my group had done this in collaboration with a group in China back about 5 or 6 years ago. And the challenge we had is that the triplet energy transfer reaction was kind of sluggish. So that was hard to work with, because the lifetime was not as long as we'd like it to be. Because the TADF in a lot of organic molecules really shortens the lifetime a lot. That's the problem. In the zirconium, like even with TADF going on, it's still 350 microseconds, which is just crazy. So that really is the defining parameter to start with. And I think, yes, if you have TADF with organic molecules where the energy gap between the singlet and triplet's a little bit bigger, that'll give you a longer lifetime. And that's probably a little friendlier for doing photochemical upconversion sensitization. At least that's my take on it so far.
So are there other questions? Yes, so Luis, please ask your question.
Okay, you can hear me?
Yes.
Yes.
Okay, thank you for the presentation. It was really interesting. Actually, I'm a PhD student in the EMT Atlantic here in France, in Brest. I'm using this technique. I'm using a photoresin that use this technique. I'm in the field of micro nanofabrication, but I'm struggling a little bit using this photoresist, because I have really bad axial and lateral resolution. I'm still, I don't know, it's because of the acrylates or because of the other molecules I'm using. I didn't fabricate or I didn't synthesize the molecules. So basically, I mean, it's really general question, but do you think that this problem of resolution is because of this system is not prepared or is not ready to have a really, I mean, I would say really high resolution?
Yeah, okay. I think I understand what you're getting at. So the advantage to using, you know, photochemical upconversion sensitization in this case is, in my opinion, because of the fact that the actual electron transfer reaction is relatively inefficient. So that allows you to grow the object slower than if you would normally do something where you make a lot of radicals in close proximity and you just get really fast, uncontrolled polymerization.
Mhm.
And then that tends to like overwrite the areas you're hoping to do the, you know, that you're hoping to like write within. And I think that's really all it is that this is a funny advantage to this, is that because it's relatively inefficient, it gives you, I think, really good control over the mechanical properties and over the spatial resolution. I think T can probably answer this better than I can. I think we were limited by the type of microscope we had. So we couldn't go any smaller in dimension, but I do think you should be able to if you have a better optical microscope. I think the one we were using was kind of on the older side. But this is good news for someone like you. Zinc tetraphenylporphyrin is commercially available and it's super cheap.
Mhm.
The acrylates are commercially available and they're also super cheap. So it's very easy to just try it if you're so inclined. That's what's good about that paper, is that anybody can do that.
Okay, thank you.
Frederic, yeah, you can proceed with your question.
Very nice conference. Maybe it's a naive question. You showed very high upconversion yield, but I think this was solution chemistry. Is that an issue for any practical use, and are there maybe tricks to maybe move that chemistry into kind of solid state chemistry?
Oh yes, yeah, absolutely. So so my group, I didn't talk about any of that because of the time. But my group started doing this with Chris Vader back in like 2006. And what Chris Vader taught me very well is, as long as you use low TG materials that are very rubbery, that is ideal. So materials that really promote diffusion, you can get this photochemical upconversion to work at pretty high efficiency. And I have all, I'm happy to send you the slide deck so you can kind of see the materials, but we were using really bad polymers initially, and then we started to learn how to do this really better. And the best material we ever found is this stuff that's called ClearFlex 50, which is you buy the monomers from this company and then you mix them together and it gives you this like beautiful, totally optically transparent rubber that is magical for hosting this upconversion photochemistry. It really worked. I mean, we had efficiencies that were over 20%, I think, at the best, and they really are good because you can shape them any way you want. But ClearFlex 50 is the one that I remember being the best. It's been a few years since we've done this because Chris moved to Fribourg, and then we stopped kind of working together because it was too hard to keep it up.
Okay, yeah, thank you very much. So you can use this kind of chemistry in, let's say, device like fields, or you would just put on a beam line and just upconvert, so without problems apparently.
Right. Yeah. People have done a lot of creative posting in polymers inside micelles, inside oil emulsions. It's like there's a lot of like real creative sort of soft materials that people have played around with. And that's the good thing, is all of these solution-based, compositions readily translate into all of these, soft materials very well.
Excellent.
So
thank you very much.
yeah, thank you.
So are there other questions? So if not, well, Phil, thank you very much for giving this lecture. Thank you, Clotilde, for the short communication in introduction. And thank you also, Phil, for accepting to discuss with the PhD student of the Institute, just previous to the talk. So thank you for all this. And
Happy to do it. Thank you very much for the invitation. I enjoyed meeting with a lot of you. So, and good to see a lot of old friends on the call too.
yeah, they can even show their face, huh? I don't know if they're still there.
Thanks, Jan. It's kind of like I miss all the times where we're at conferences and, we just can, talk in the hallway, have coffee, all these things that we always are used to doing. And it's just been way too long. So.
Okay, so thank you very much.
Yeah, thanks everybody. I know it's late in France too, so have a good evening.